any matrix A, and you can rewrite it as P inverse J P, where J is the Jordan form of A. And the Jordan form of A is it's a very nice matrix. It's a block diagonal decomposition where the Jordan blocks reflect the eigenvalues of the matrix. And if the matrix is diagonalizable, then the Jordan block is just a diagonal matrix.
Okay.
Simple. This actually is a Jordan matrix already. But here's the cool thing. If you have E to the TA, all right, there's a trick you can do. Check this out. You can do E to the TA minus lambda I plus lambda IT. See, I can add and subtract the identity matrix times the lambda. I'm not saying what the lambda is. I'm not even insisting that lambda is an eigenvector. I mean, an eigenvalue for the matrix. I'm not even insisting it's real. It could be complex, whatever. The thing is then, this matrix is a multiple of the identity. Therefore, it commutes with that, no matter what it is. Identity commutes with everything. So this we can rewrite as E to the lambda IT times E to the T times A minus lambda I. Like that. But then by the homework problem I just told you guys about, we can factor the E to the lambda T out. That's just the ordinary garden variety, plain old E to the eigenvalue times time, okay? And then that is going to be the identity matrix plus T times A minus lambda I plus 1/2 A minus, T squared over 2 rather, A minus lambda I quantity squared, and so forth and so on, higher powers. I refer to this as the magic formula because it's where the magic happens. Because this formula makes manifest why eigenvectors are so neat for the matrix exponential. See, because what happens when you hit this matrix exponential with an eigenvector? Like let it operate on an eigenvector, what happens? It's right, you get E to the lambda T times IU, right? I'll write it out for the sake of anybody who doesn't see it, what you saw already. And then higher order things, right? But as you said, this is 0. And that's 0 too, because it's 0 after the first application of the matrix. Yeah. So yeah, this is just straight up the eigensolution that we already talked about. What's neat, right, is that if you have a Jordan chain, it works in conjunction with the magic formula. So like if for this matrix, E to the, this matrix here, right, this E to the A right here, this one, if I do that one, and I do E to the TA, yeah, times, let's say, oh, I don't know, E2, what happens to it? So we've got, and so for this one, I'm going to use the eigenvalue. What is the eigenvalue for A? It's diagonal. The eigenvalues are on the diagonal manifestly, they're 3. So I'll do E to the 3t times what? Times I plus t times A minus 3I, right? Plus t squared over 2, A minus 3I quantity squared plus stuff. Let all that operate on E2. What happens? Well, just like we have see we wrote over here, right here, right? That's 0. And all the higher order terms in that series are 0 as well, see? So the magic formula truncates when it operates on a Jordan vector, on the highest, like a Jordan chain vector that is subject to these Jordan chain conditions. And I'm not telling you quite enough for you to completely grasp it. Like you need to work homework on these and stuff to really get it, you know, but E2 plus, what is that? T times what? What's A minus 3I times E2? Remember, it's E1. Yeah. And there you go. That's one of the solutions here. Manifestly, it's this. It's t e to the 3t and then e to the 3t. That solves, so if I set this equal to xy, like so, that solves xy prime equal to, 3, 1, 0, 3 times xy. It's pretty easy to see it solves the second equation. The second equation is y prime equals to 3 times y. Well, if y is equal to e to the 3t, then it's 3e to the t. Now, how about the first one? 3 times x, well, that's 3 times t to the 3t, right? And then, so you got 3e to the t, excuse me, you got 3te to the 3t, plus e to the t, plus e to the 3t. Is that equal to the derivative of x? Well, the derivative of te to the 3t is, yeah, it's 3te to the 3t plus e to the 3t. Yeah, it works. You can derive the t in the repeated root solution. You know that t that we say, well, if you have the characteristic solution is repeated, where does the t come from? Well, one answer you can give is it comes because if you look at the corresponding system, it's not diagonalizable. In fact, you require a generalized eigenvector of order 2 to solve that, and that will bring the t times the exponential into the solution by this mechanism. So there are, at least, I would say, 10 different ways to explain where the t is coming from in the double root solution. This is one of my favorite. So basically what I'm telling you is to solve dr dt equals to ar, to actually do it, right? If you can learn how to find a Jordan basis for the matrix where your Jordan vectors are arranged in these like chain conditions, then you can just feed those to the matrix exponential and it'll pop out solutions for you. Now, the complication here that I have not made manifest is that sometimes the eigenvalues are complex, and in that case, you have an abundance of riches. You don't get your complex eigensolution as a pair of real solutions, and you can even have complex generalized eigenvector solutions, and those, again, will pick up like pairs of sine, cosine times exponential terms. But, it usually beats the pants off of just trying to calculate the matrix exponential directly. And there's also methods to solve non-homogeneous problems, right? I'm just talking about the homogeneous problem right now. But yeah, this is why the matrix exponential matters. Systems of differential equations, it gives you the general solution set. And notice that the analysis that we started today with was completely general. It works, that converges for any matrix, any system. Yeah. So I think it's pretty nice. All right, so next time I will behave. I will get back into your, I'll get back into, I'll start chapter 2 and we will do the Lebesgue. I seem to have gone 9 minutes over, my bad.